Stevenson. In this video, we'll be going over problem 8 to however far I get before my pen goes wacko. In this problem, we're told that a ball of mass 2 kilograms, so we know that this is 2 kilograms, falls vertically, so it's falling down, and hits the ground with a speed of 7 meters per second. And then it hits the ground and rebounds with a speed of 3 meters per second, right? And we know that this is the same ball, so it should have the same mass. I think we're asked to find out the magnitude of the change in momentum of the ball. So we want to find the change in momentum. The magnitude just means that your answer is always going to be positive. All we care about is the size, not the direction, right? So, for example, the momentum here in this before, so I'm going to say the momentum, actually momentum is P, right? Momentum before is, remember momentum is mass times velocity. So the mass is 2 times the velocity. Let me just go ahead and put units. It's always a good idea. Times, it's actually -7 kilograms meters per second. Not kilograms, meters per second. Right? So this has a momentum of -14 meters per second. That was before. Right? And then after it hits the ground, it now has a momentum, kilogram meters per second. That's momentum. This one has a momentum of 2 times 3, and in this case, the 3 is positive because it's going up, and here we get 6 kilogram meters per second. So the change in momentum is just like, what is the difference in momentum? So we went from -14 to 6. So you can just think, well, how do I get from -14 to 6? How much did it change by? Or you can actually say, okay, well, change in momentum is going to be momentum before minus the momentum after. Or actually, it's better to do momentum after minus momentum before. That's typically how we do it, although it doesn't matter. So then we get 6 minus -14, which is 20 kilogram meter per second. And notice how the units are Newton seconds. That's another way to measure momentum. To get to Newton seconds, you could just imagine a Newton is a kilogram over meters per second squared. So if you just multiplied a Newton times what we have here, the seconds would cancel out and you end up with this, right? So the answer is 20, which is this one. Another way to find that, like I said, if I did this backwards, if I did before minus after, then I would have gotten 6. I would have got -14 minus 6, which I would have gotten -20. And that's where this thing of magnitude comes in. If we're talking about magnitude, we don't care about the direction. So we would just say, oh, well, that's just 20 if I don't care about direction. Kind of an extension of this is knowing that change in momentum is the same thing as impulse, where impulse is actually force times time, right? So we knew the change in momentum was 20 Newton seconds, which is the same as impulse, which is force times time. So if I knew either force or time, I could figure out one of the other things, right? So for example, I know that this ball was in contact with the ground for, let's say, 0.3 seconds. I'm just kind of making this up right now, but that might make sense. Then I could figure out with how much force the ball hit the ground, right? So like you can imagine if you're trying to see like, is it going to crack the tile or something, that might be, you might figure that out by how much force it was. So in this case, that would be force times 0.3, or I take 20 over 0.3, right? And this is Newton seconds over seconds. This is 0.3, and you would get that's how much force in newtons the ball hit the ground with, right? Likewise, if I told you the force that it hit the ground with, you could figure out the time, all right? So just be ready for things like that, knowing that change in momentum, like we found here, is the same thing as impulse, which is impulse is also force times time. Okay, next part is we're driving a metal bar into the ground. One way to do this is to drop a heavy object on it, right? So here's your heavy object. It has this mass, which is the same as 2 times 1,000 or 2,000 kilograms, right? You got to know your scientific notation, which hopefully you do by now. The bar has a mass of 400 kilograms. And we're trying to, all right, they're just repeating this. They're saying the object strikes the bar. So when it hits, it's moving at a speed of 6 meters per second squared. Sorry, 6 meters per second, that's a velocity. It comes to rest on the bar without bouncing. As a result of the collision, the bar is driven into the ground a depth of 0.75 meters. So this is a collision, right? A collision is happening. It doesn't bounce, right? So you have to think, when it doesn't bounce, what kind of collision is that? And then we're trying to determine the speed of the bar immediately after the object strikes it. We want speed. Okay, so because they stick together, that means there's always conservation of energy, but it means it's an inelastic collision. It's not conservation of energy, conservation of momentum. So the conservation of momentum says the momentum before. So remember, momentum is mass times velocity. So the momentum of the falling object before is its mass of the object times its velocity, and this is the mass of the bar times the velocity of the bar, right? This is the total. You have to think about the whole system, right? So this is the total momentum before, and the total momentum before should be equal to the total momentum after. And so afterwards, because they stick together, the mass is going to be basically the mass of the object plus the mass of the bar times the velocity of those two objects moving together, right? And we know a lot of this stuff, right? The mass of the object is 2,000 kilograms. The mass of the velocity of the object is -6 meters per second. Why negative? Because it's going down. Plus the mass of the bar is 400, and the velocity of the bar is 0. And then afterwards, we know the mass of the object is 2,000 plus the mass of the bar is 400. And what we really want is, we want to know the final velocity, right? So that's what we're looking for. And so we can do this. This is just 0. 2,000 times -6 is -12,000 kilogram meters per second, or you can convert that into Newton seconds. And that's going to be equal to, this side is 2,400 times VF. And remember, now you notice this is kilograms, right? The only thing missing is VF, which is the final velocity. So if we do this, we're dividing both sides by 2,400 kilograms. So we'll have -12,000 kilogram meters per second over 2,400 kilograms, right? Your kilograms will cancel, and -12,000 divided by 2,400 is -5 meters per second, and that's your final velocity. That's how fast these objects are moving together after this strike, at the moment after it strikes. Yes. So then you might check the answer key and say, hey, but the answer key is not -5, it's just 5. And why is it just 5? Well, because they're asking for speed. And speed is like the mathematical way of doing this. Speed is just the absolute value of velocity. And the physics way of thinking about it is velocity is speed with a direction, right? The negative means we're going down. Then speed does not have a direction, which means if I just want to know the speed is just 5, because we don't care what direction it's going. So the speed would just be 5. Whereas the velocity is -5. The -5 tells us it's going downwards. All right, the next one is determine the average frictional force exerted by the ground on the bar. So we're going to have to talk about some energy here. Okay, B is a little bit tricky, but we can figure it out. Determine the average frictional force exerted by the ground on the bar. So we want to know how much friction was exerted on the bar by the ground. And the way we're going to do this is we're going to think about friction, the work that friction does. So remember, work is usually force times displacement, but there's also something called negative work. And negative work is when something resists motion, right? So friction is a type of negative work, right? If you're pushing on a block with 50 newtons of force, and there are 30 newtons of force pushing back, right? This is doing negative work because it's preventing this 50 newtons of force from creating as much momentum, as much kinetic energy as it could have, right? So this friction is acting as negative work, right? So what we want to think about is another way of thinking about work is, remember, work is how much energy. It's not energy, but how much energy is required to do something. Another way to think about work is the change in kinetic energy, or the kinetic change in potential energy as well, if you think about it. But in this case, we're going to talk about kinetic energy because we don't know the height of these things. If we think about change in kinetic energy, that's the same thing as work. So what we want to think about is we're only talking about once this object hits, right? As soon as this thing hits, it's moving at 6 meters per second, right? So the kinetic energy initial kinetic energy, here goes my pen. See if I do it down here. The initial kinetic energy is, remember, kinetic energy is 1/2 mass times velocity squared. So it's 1/2 times, those two objects are together when it starts, so it's 2400 times 5 squared. Technically -5 squared because it's going down, right? Now if you do this, you get 1200 times 25, which, let's do that real quick. 1200 times 25 is 30,000, right? So the initial kinetic energy is 30,000. Now this is kind of easy because what we know is that it comes to a rest, and then the bar is driven to the ground at a depth of 0.75. So the bar initially goes into the ground and stops, right? So the final kinetic energy, oh man, come on. Okay, hold on. Okay, let's see if this works. The final kinetic energy is just 0, right? So the change in kinetic energy is just going to be 30,000. And remember, these are joules, right? We measure kinetic energy in joules. So change in kinetic energy is 30,000. Remember that work is the same thing as change in kinetic energy. So our work is 30,000 joules. And then remember that work is just force times distance, right? And our distance was 0.75. And then therefore the force would be 30,000 divided by 0.75, which is 40,000. Right? And so this is our average, this is the force, in this case, of friction, right, that worked against our kinetic energy, right? Because we started with 30,000 joules of kinetic energy. We ended up with 0 joules of kinetic energy, right? So there was some force acting against us. That force was friction, right? It's technically negative force because it's stopping motion, right? And so we know that the work is 30,000, and we can then set this formula for work equal to 30,000, plug in what we know, and end up with our the force that friction exerted. Okay, so number 10, we're trying to figure out the force, average force needed to accelerate a 7-gram pellet, which is 0.007 kilograms. Remember, you always need to be in the appropriate units, otherwise it's going to get messy. From rest, which is 0 meters per second, to 175 meters per second over a distance of 0.7 meters along the barrel of a rifle, right? So you might think, oh, force equals mass times acceleration, right? And you can be like, okay, well, oh, come on. Force equals mass times acceleration. And you might think, okay, well, acceleration is just change in velocity. So the velocity changed by 175. The problem is we don't know the time, how long it took to go from 0 to 175. If we knew that, which we actually can calculate that, I think, after this, which maybe I'll do that. If we knew that, then we could figure out the acceleration that way. And we could also plug in the mass, and we can know the force already. But we don't know the time, so we can't do it this way. So what we need to do is we need to find another equation, right? And so what we could do is we could figure out, again, using kinetic energy. The initial kinetic energy here is 0, right? It's starting from rest. So the initial kinetic energy is 0 joules. The final kinetic energy is 1/2 times the mass times the velocity, which is 175 meters per second velocity squared, right? So if we do this, 1/2 0.5 times 0.007 times 175 squared, we get 107.188. That's rounded. This is our final kinetic energy. It also turns out to be our change in kinetic energy because the initial kinetic energy was 0, right? So that's our change in kinetic energy. Remember, change in kinetic energy is also the same thing as work, and work is the same thing as force times distance, right? A lot of physics is just connecting all the things we know, right? So this is our change in kinetic energy. We can go ahead and set it to force times distance. We want to know the force. We know the distance is actually 0.700 meters, and so we could divide both sides by 0.7. And you would get 153.125 newtons. All right. Okay, for 11, you're asked to draw a free body diagram. You need to go back in your notes and look how to do this, but we'll do it here. First one is a box at rest on slope. So free body diagram is just trying to draw what forces are acting on an object at a single moment in time. So here's our object. It's at rest on a slope. So the forces acting on this are gravity. Gravity pulls this object straight down towards the earth, right? So the earth is down here. This is the force of gravity, right? Also, this box is not going to sink into our surface because there is a normal force. The normal force always pushes perpendicular to the surface, right? So this is our force, our normal force, or sometimes called the support force, right? That's not enough, right? Because if that was the case and there was no friction, this box would also be sliding down this. There's also a force of friction that's holding this box because it's at rest from moving down the slope. And there is no forward force here, right? Because otherwise it might be going down. What's a little bit tricky is when you get into more advanced physics, these two vectors here should cancel out this vector, meaning if you added them, right, if you put them tail to tail or head to tail, this vector here would be the same as that in a negative way, right? But again, that's outside the scope of this class. But if you are planning on taking physics next year, you would need to know something like that. Next one is a car moving at a constant speed horizontally. So here's our car. The nice thing about free body diagrams, you don't have to draw them nicely. Let's be really precise about this. So here's a simple one, which would be okay, right? Here's your car. The force of gravity is going to pull you down. The normal force should be, notice these two are the same size. The normal force should be the same as the force of gravity because the car is not sinking in, right? Now we're not negating friction, right? So if you negated friction, you could say, okay, well, that's enough. It's just going to keep moving because object in motion stay in motion. But we should also say, well, there is some friction pulling this thing back. Friction's not going to be as great as gravity. So I'm going to make this a little bit smaller. This is the force of friction. If you want to say kinetic friction, that's good because it's moving. And if it's moving at a constant velocity, then the net force in this direction must be equal, which means the applied force must be equal to the frictional force. And so that would work. A better example would be actually drawing this car, because there is something a little bit different going on. I'm not going to draw a real fancy car, but there's my car. The force of gravity pulls down on this object, right? And so, sorry. Oh, come on. So that force of gravity is pulling down on the entire object, but it's also just on each wheel, right? And then the support force is each on each wheel as well, which is equal to gravity. So there's actually kind of two vectors there because each one of these wheels has it. And then you also get the frictional force and applied force. That might be a more complex one where you take into account the fact that that force is split up between these two tires, these two wheels. Okay, number 12 is actually something that we did not have time to cover in class. And so let's consider it like a bonus question. It's not very difficult if you have the formula, it's just plugging it in. So it is something expected of you to do. Basically, that formula is here. It will also be given on the test. What it says is the force felt by gravity is equal to G, which G is this constant, it's a gravitational constant, times mass 1, which would be like the first body, in this case Mercury, times mass 2, which is the mass of the second object, which in this case is the sun, divided by r squared, which is the radius, the distance between the two. Right, so this is very, very simple if you have a calculator. Right? Just plugging in, determine the force between Mercury and the sun. You're just plugging in G, which is 6.67 times 10 to the negative 11. And then you're going to multiply that by the mass of the first one, which is 3.3 times 10 to the 23rd. And then you're going to multiply that by the mass of the second one, which is 2 times 10 to the 30th. And then you divide by the radius squared, like how far apart are they squared. So 5.979 times 10 to the 7th, and you're going to square that. And if you have a decent calculator, this is very easy to plug into your calculator. Maybe I'll try to get Desmos up and show you. Okay, so I already did this on Desmos. You can see what I entered here. And you can see the result is this, right? So the force felt by the force of gravity between Mercury and the sun is 1.3 times 10 to the 28th. It's quite a lot of force, right? Felt between those two objects. But again, it's really easy just plugging it in. So if you get a question like this on the test, just plug it into the formula. It shouldn't be a big deal. Okay, in this one, number 13, we're looking at a weightlifter. He has lifted this 2,250 Newton above his head. I guess so this is its weight, not its mass, right? And we're assuming, I guess, that he's on Earth. The weight is held still, so he's not moving, right? For the first one, in the box are the names of 3 forms of energy. Which one of the forms of energy does the weight have? So kinetic is energy of motion. This thing is not moving, right? It's held still, so it's not moving, so no. Sound energy is like if, when I'm talking, there's energy waves coming out of my mouth. When you smash somebody on the ground, there's energy waves that come out as sound. Gravitational potential is what it has because it has height against gravity, right? You've lifted this thing a distance above height against the gravity of Earth, right? So this thing has gravitational potential energy. It's a very basic question, right? You should get that one right. What force is used by the weightlifter to hold the weight still? He is using, what force is used? He's using applied force, right? He's holding it up there using his body, which is applied force. And then it says, what's the size of the force? Well, in order for him to hold it there against gravity, right? It's just like as if it was sitting on a table, right? Imagine it's sitting on a table. You know that gravity's pulling down on it. How hard does gravity pull down on it? Well, gravity's pulling down on it as hard as much as it weighs, right? That's what weight is how hard gravity pulls down on you. And so there must be an equal or opposite force called the normal force or the support force that is equal and opposite to the gravitational force, right? So the size of this force is the same, 2,250 newtons. That's how much a force you must apply to keep it up there. Giving the reason the answer is what I just said. To lift the weight, the weightlifter does 4,500 joules of work in 3 seconds. Calculate the power developed by the weightlifter. Remember, power is work over time. Right, so in this case, he's doing 4,500 joules of work over 3 seconds, which means he's doing 1,500 joule seconds, which is better known as watts of work. If the weights only required 3,100 joules of energy to be lifted, determine the efficiency of the weightlifter. So efficiency is power out over power in times 100, right? So it only required 3,100. He had to put in 4,500, right? So we're doing 3,100 divided by 4,500. That's 31 over 45 times 100, which is 68.89%, right? So it's about 68.89% efficient. That's the end of that question. Okay, number 14. We're looking at a table which shows braking distance, speed, and kinetic energy, right? So imagine the car is going 10 meters per second. You could calculate that it has, if you know its mass, or actually we can go backwards and calculate its mass, but you could calculate the kinetic energy is 40, and then the braking distance would be 5. Meaning if you slammed on the brakes, it would take you 5 meters to stop. This question actually tests a little bit of your math knowledge as well. A student suggests the braking distance is directly proportional to kinetic energy. What it means to be directly proportional is that means it has to go through the origin and it has to be a straight line, right? You can't have a curvy thing. If it's curvy, it's not directly proportional unless it's like a power proportion. And also if it's like a shift up here, then it's not directly proportional. So the first one is just graphing. Again, math knowledge. We're trying to graph braking distance versus kinetic energy. You see the braking distance down here. It looks like we're going to be counting by tens. Right, this is just basic math knowledge. Here we got to get up to 360, 100, 200, 300, 400, 500. Maybe if we count by 50, 100, 200. I guess we got to count by 100s in order to fit all our data on there. We're just going to graph some points. 540, so 1, 2, 3, 4, 5. 40 is 1, 2, 3, 4 right there. And we practice graphing in some of our lab stuff, right? 1290, 12 and 90 is there. And 20, 160, 20, 110, 120, 130, 140, 150, 160. So far it looks pretty good, but maybe not. 33, 250. 31, 2, 3, 250. It's right there. And then 45, 360, 45, 360, 1, 2, 3, 4. Make sure I did this one right. This is the only one that looks off. So 33, 250. 33, 1, 2, 3, 4, 5. All right, so what do you think? Does it look like a straight line? Does the graph show that the student's suggestion was correct or incorrect? Give a reason for your answer. So what do you think? Does it look like a straight line going through the origin?